This is a video about electric fields. Now we've been talking about electric force, electrostatic force, and comparing it to our gravitational force. We had this setup that looked like this. We said if we had a planet and we stuck an object nearby it and that had its own mass, and we stuck that at some distance r from the planet, let's give this thing a mass of capital M, that we had a force gravitational that was equal to g times mass of the planet times mass of the object over r squared. Then we did the same thing where we said this was some charge q, and here we are some distance from the center, r, and we're going to put an object there, and we said we got an electrostatic force that was k q over r squared. In both of these cases we have one piece that is specific to the object that we're putting at that location, and then all the rest of it is kind of just an environmental item. If I put a different item here, a different object with a mass of double that, then I would get double the force. If I put a different mass at the same location, a different object at the same location with double the charge, I would get double the force. So there is a quantity that's the same for any object that I put at that location. And then to find what the force is, I'm just going to multiply that quantity by the mass that I'm putting there, or over here by the charge that I'm putting there. With gravitation, it's a little bit easier to see because we can say a sum of force equals mass times acceleration, which we know. So we have something like an acceleration that would be our gm over r squared, and that's kind of an acceleration field, right? When we are in, that's specific to one r value, and when we're near the surface of the earth, then this thing comes out to be something like 10 meters per second squared. Well, here we're going to do something like that too, but we are going to define an electric field as being kq over r squared. When we do this, and we give this units of newtons per coulomb, when we do this, we are setting ourselves up well to be able to say our electrostatic force is then equal to the object that we put at that location's charge times the electric field. Now when we said F equals ma, that was actually pretty easy to work with because mass was always a positive number, so our force always pointed in the direction of our acceleration, or the other way around if you want to say our acceleration always pointed in the same direction as our force. With this, charge can be positive or negative. So if I've got a charge that's sitting here like this, big charge, and I'm going to nail that one down in place, and I put another charge somewhere nearby, if this is a positive charge, it's going to feel a force that points straight outward. That's for force. If I take away that charge, there should be something left there, right? If I pick something here with a charge of 2q, I'm going to get double the force, but that's going to go out this way. Now if I get rid of the charges that are there, there's nothing to experience these forces anymore, so now these are going to be electric fields. So an electric field in some way is an electric force without an object there to experience it. Then I want to talk about how this works. So electric field is a vector, which means if I've got multiple points, right, if I've got a positive charge sitting here and a negative charge sitting here, and I look at some location here, at that location I'm going to get an electric field this way from my positive charge. I'm going to get an electric field this way from my negative charge. And you can think of these electric fields as being the force that a positive charge would feel at that location. So with a positive contribution, I'm going to get a push. A positive charge will always be a pusher of fields. A negative charge will always be a puller of fields. So this negative charge is like pulling on this spot. That's getting a negative inward bound electric field. This positive charge is pushing on this spot, so it's getting a positive outward pushing electric field. Now the electric field at this location isn't this, and it isn't this. It's the vector sum of these. So I'm going to get something that points probably about like that, E total, at that location. When I have just a positive charge sitting somewhere, it puts out electric fields that are radially outward from itself. And when I put a negative charge, it's going to look very similar, but it's going to give radial fields that are inward. So an electric field from a positive charge will always push outward, meaning a positive charge is like an electric field pusher. An electric field from a negative charge will always pull inward, so a negative charge is like an electric field puller. Now this right now, the way I've got this drawn, is saying there is no connection between these at all. They can't see each other. But what happens if they can? If I take this negative charge and I move it over close to the positive charge, like this, I have now created something called an electric dipole, which is a name that probably doesn't need a whole lot of explaining. Near each charge individually, the electric fields do act like this. So I would say probably outside of those lines, even outside of those lines, the electric fields do behave like this. In between, I've got a little bit more going on, and I have to really consider adding them. If I pick a location here, that's going to look like this up here. So I'm going to get an electric field vector that points from my vector sum that points something like that. If I pick this spot, I'm going to get an electric field that points something more like that. If I then go through and pick all the spots and draw my field vectors, I would end up with, well, a mess for one thing. But if I draw these spots really close together, right, I drew that spot, now if I draw this spot, I'm going to get something that's a little bit more this way. If I then, instead of looking at individual points, just kind of want to draw the overall trend, what I'm going to get is fields that more or less look like this. Now, of course, field vectors themselves at individual locations can't be curved, but what's going on is I've got this one, and this spot, and this spot, and this spot, and as I take a bunch of those and put them together and just kind of connect the dots, I will end up with electric fields that look like this. That's the idea of electric fields. That's all that we're really doing with this, is finding is finding what sorts of fields these push out or pull in. My electric force is going to still be a Q times an electric field. So if I put a positive charge at this location, it's going to actually more or less follow that field line and be pulled in. If I put a negative charge at this location, a negative charge, right, if this is a negative number, then these two vectors point in opposite directions, which means this is going to end up following this field line and go in the opposite direction, more or less. When I say more or less, I just mean that's the direction of the force at each point, not the direction of the velocity at each point. So we're going to probably not follow that field line exactly, but we're going to move in that general trajectory inward. That's electric fields.